In the previous lesson, we showed how the electric field lines compare to the lines of equipotential for a positively charged electric monopole. The electric field lines point radially outward, whereas the lines of equipotential are concentric circles. If this is viewed in 3D, then these lines of electric field pointing outward radially point in all three dimensions, the x, y, and z axis, and therefore these aren't really lines of equipotential, they're surfaces of equipotential. And so we say that the equipotential this arrow is pointing at is at a relatively high potential, and this one, we'll label them A and B. Equipotential A is relatively high, and equipotential B is relatively low. Electric field lines always point from regions of high potential towards regions of low potential. Also make note that the electric field is a vector, but and you see that because the indication of the arrows. Lines of equipotential are not vector quantities. Electric potential is a scalar quantity. Electric field is a vector quantity. Okay, well, then there exists a difference in electric potential between surfaces A and B. It took me a while to write that. Difference in electric potential. So I don't want to have to write that every time. There's a word that replaces that. It's called voltage. Okay. So as long as you have a difference in electric potential, you have the ability to drive an electric current. For example, a standard AA battery looks something like this. And you probably know the value of the electric potential difference. In other words, the value of the voltage. These AA, AAA, C and D batteries. Some are bigger than the others, right? This might be a D cell battery. This might be a AA battery. This one just has the D has a longer life to it, but they both have the same electric potential difference. That has to do with the electronegativities of the chemicals that are used to make them. There's the high potential, there's the low potential, and the difference in electric potential in either case is 1.5 volts. Voltage is difference in electric potential. If I connect a wire here, wherever I touch this wire, I create a region of high electric potential. Wherever this wire touches, creates a region of low electric potential. Okay. So we can see the difference in electric potential in a demonstration with the Van de Graaff generator and a fluorescent bulb. The only way this bulb is going to light up is if there's a voltage across its ends. There has to be a difference in electric potential from one end to the other. So if I place the bulb like this, if I set it here next to the Van de Graaff, then it shouldn't light up at all. If we draw in the electric field lines, and I draw one of the lines of equipotential, well, if I got it right, then this is sitting so that its two ends are both at the same electric potential. So although there is a value of electric potential, there's no difference in the electric potential, and the bulb will not light up. But if the bulb is in this orientation, then one end is at this electric potential, the other end is at a, well, if this is positively charged, then this is at high electric potential, this is at low electric potential, and so that difference in electric potential provides the voltage that will light up the bulb. So there I have another video lesson where I show this demonstration, and you can see that indeed that's the case. So thanks for watching.